Good afternoon everyone, I am Mr. Ish. Thank you for joining me for this video on inverse hyperbolic integrals. This is a topic that you should just be generally familiar with. You probably don't have to delve into this topic too deeply. Let's get a few terminology things out of the way. You know, when we're talking about trigonometric functions, they're related to the unit circle. When we're talking about the hyperbolic functions, they stem from and are related to the hyperbola. When we look at the inverse trigonometric functions, if we have something which is sine x, the inverse of this becomes inverse sine of x, or you can say arc sine x, and I'm just talking about this generally. When we look at the hyperbolic version, you have hyperbolic sine, and then the inverse of that becomes this, but you can also abbreviate this as AR sine hx. See the difference? Here you have an arc, here you have an AR. There is no C over here. That again stems from the difference or the relationship that these have, and the inverse and the regulars with the unit circle and this and its inverse, and the associated other hyperbolic functions and their inverses with the hyperbola. So don't make this error in judgment that you're putting an arc over here when you're talking about inverse hyperbolics. You can either go with this or you can go with that. Keep in mind also this, that we've looked in the previous video at the derivatives of these inverse hyperbolics. When you're looking at inverse hyperbolic sine, and it's important to remember these or to know of them, you're looking at something which comes out as this 1 plus x squared or x squared plus 1. The derivative of the inverse hyperbolic cosine is 1 over square root of x squared minus 1. And lastly, because these three, the sine version, the cosine version, and the tangent version, the inverse hyperbolics of these are the most important with derivatives and with the integrals. When you're looking at the inverse hyperbolic tangent, we have a derivative which comes out as this 1 over 1 minus x squared. So why is knowing these three right here important? Simply for this reason: if you saw hypothetically a question which looked something like this, you could think of this, and you can think of the fundamental theorem of calculus, inverse relationship between the derivatives and the integrals. If this has a derivative of this, the integral of this will take you back to that. So if you see something like this, you can actually jump to this as your answer, or you can just say AR sine hx plus c, that this right here is an acceptable answer. If you see something like this, you could have a different type of answer. You can use trigonometric substitution technique, where you're looking at something which has the format a squared plus x squared, and that leads you to the tan substitution, and you can go that way, that route. But if you see something like these as integrals, you can think of these library of antiderivatives, and you should be going back to these. In each of these instances, you can go back to that if you saw something like this based on the circumstance of that question. In the remainder of this video, I'm going to show you, if supposedly, how you would derive the integrals or the antiderivatives of these functions. We're not looking here in a backwards trend where you're having this as an integral. You just go backwards and that's your answer, your antiderivative. But if this right here, these three serve as your integrands, how do you derive an antiderivative of these? The three most important integrals to look at are these: the inverse hyperbolic sine, inverse hyperbolic cosine, and inverse hyperbolic tangent. And you can use integrating by parts technique to do this. If u is equal to your function which you have right there, inverse hyperbolic sine du is equal to the derivative of this, which you now know as 1 plus x squared dx, and v is the integral of what remains right here, x. You know this, you've seen this. Technique is excellent for inverse trigonometric and inverse hyperbolic antiderivative formation. uv minus integral v du, you'll have an x, you'll have an inverse hyperbolic sine x minus v, or here's x, du is 1 over root 1 plus x squared dx. You can do polynomial substitution to get rid of this. If a is equal to 1 plus x squared, dA is equal to 2x dx, and dx is equal to dA over 2x, and you can modify this entire expression. You can bring the 1 over 2 out, you'll have an x, you'll have a dA over x, and then you'll have a root a over here. The x's cancel out, you can cancel them out. Everything over here becomes this, minus 1 over 2. You can bring the a up as a to the minus 1 over 2 dA. Just easily integrate this and take this to completion with resubstitution for this, and we will have as our antiderivative for that inverse hyperbolic sine to be this. And that right there is our answer. For the inverse hyperbolic cosine, it follows a very similar trajectory. You do in integrating by parts technique to start it out, and then you can do uv minus integral v du, and you plug in these items. You have x for my v, and then u is your inverse hyperbolic cosine, and then you do minus v du. V over here is x, du is this 1 over root x square minus 1 dx. And now you have to do polynomial substitution to handle this. A is equal to x square minus 1, dA is equal to 2x dx, and dx is equal to dA over 2x. With these substitutions, you can modify this entire expression and write it out as this. And it's not hard. This is what you get. You can rewrite it out again and cancel out the x's, bring the 1 over 2 out. And this is not very far away from completion. The x's cancel out. You have a root a, which you can bring up as a to the minus 1 over 2 dA. When you integrate all of this, n plus 1 divided by n plus 1, this right here will be your final answer, and I'll post it here for you. The antiderivative of that inverse hyperbolic cosine will be, and this would be a good antiderivative for that. The inverse hyperbolic tangent follows a very similar path. Again, you do your u, du, and your v substitution. U is your inverse hyperbolic function. You know the derivative of that. V is the integral of dx, and you just get an x from there. Then you have this uv minus integral v du template into which you plug in these items. You'll have a uv, which is just x tan h minus 1 x. Here I'm really doing vu, but uv, vu, it's all the same. From here you're getting an x, and then the du is 1 over 1 minus x squared dx. You have to do polynomial substitution to handle this. If a is equal to 1 minus x squared, dA is equal to minus 2x dx, and dx is equal to dA over minus 2x. And you plug these into this expression over here. You'll have x hyperbolic inverse tangent minus, and let's plug in these items. You have x over a, and then dA over minus 2x. This minus 2 can come out with here and impact it from the outside, and you end up with this plus 1 over 2. The x's cancel out. You have dA over a, which is really a to the minus 1, and you know that brings a natural log antiderivative. But let's take this to completion. Your final answer should be this: x inverse hyperbolic tangent x plus 1 over 2 natural log a, which is 1 minus x squared plus c, and this right here is your antiderivative for that integrand over there. We end this video with this one question over here just to drive a good point home. If you have that integrand over there, dx over root of 1 plus x squared, and this is something I alluded to at the beginning of this video, and we know if we have a hyperbolic inverse sine, it has a derivative of 1 over 1 plus x squared, and this thing is serving as an integrand. You can think of these in a backwards way using the fundamental theorem of calculus. Knowing that this serves as your integrand, you can work backwards, and then you know the answer to that should be r sine h x, or you can say sine h minus 1 inverse hyperbolic plus c. So if that were your question, you can say this right here is my answer, and you would be right. But the other way you can do this is by thinking of trigonometric functions. You have a hidden expression over here which looks like a squared plus x squared, and you know we've talked about this. When you look at something which looks like a squared plus x squared, or x squared plus a squared, here a is equal to 1, then the substitutions which come out from here is x is equal to a tan theta, which is just tan theta because the 1 is meaningless here, and then dx is secant squared theta d theta, and this entire expression over here can be rewritten. It can be rewritten into this form. The dx becomes secant squared theta d theta, and in the denominator you have 1 plus tan squared theta. But you know this right as a trigonometric identity, which is equal to secant squared theta. So you're essentially looking at the root of secant squared theta, which is just a secant theta. And you end up boiling down everything to this. And you can simplify that to just secant theta d theta. And you know the integral of this is easy. The antiderivative is just natural log secant theta plus tan theta plus c. So this can serve as another answer, but you also know this right here is an ambiguous answer. You have to think of everything here with regards to this. Solve for theta. Theta is equal to arc tan x. See, now we're looking at inverse trigonometrics, not inverse hyperbolics, but inverse trigonometrics. And you can map out a triangle using this. Theta is equal to arc tan x, which is really an x over 1, which is x over 1 here. And then you fill out the triangle, you have x squared plus 1. And then you plug in these values. You're looking at natural log of secant of this. The secant of this theta is going to be your hypotenuse over adjacent, which is x squared plus 1, plus tan of this triangle theta over here is going to be just x. And this right here can be another answer to that question. So that question over here, right here, has two answers. One can be this, if you're thinking about hyperbolics, inverse hyperbolics, and it can also be this in terms of you viewing this as a trigonometric integration question. So you can present both of these, and these are both good answers depending on the circumstance of the question. So keep in mind that integration questions such as these can have several routes you can take, and you sometimes may have to take both of those routes towards two different answers, though at the end they both are referring to the same thing, but you have two different approaches over here. This video is meant to be a general overview of inverse hyperbolic integrals only, and there's really no pressing need to get too deep into this topic. Thank you for watching. Have a nice day.